Today we're going to talk about mass ratios as conversions. As conversion factors, sorry. And we're going to talk about mass percentage. And empirical formulae. And just a reminder, Katie's doing study hall directly after this class, 2 to 3:30. If you want to just have a quick review before you go to wherever you're going, if you're going anywhere on spring break. Okay, can we go on to the next? Is that RICAL? Yes, RICAL, empirical. Okay, so let's talk about mass ratio. Mass ratio is the mass of one element over the total mass of the compound. So you should have your periodic tables out because they will help you figure out the masses of the elements in the compound. And what's important to know about the mass ratio is that you have to take into account all of that element in that compound. So for example, if I say, what is the mass ratio of carbon in C6H12, you have to take into account that there are 6 carbons. So what we're going to do is we're going to put the mass of the carbons on top. So we're going to do 6 times 12.01 grams per mole. And on the bottom, it's the total mass of the compound. So it's the 6 carbons plus the 12 hydrogens. So you'll do 6 times 12.01 grams per mole plus 12 times 1.008 grams per mole. And you should get 0.8560. So this is your mass ratio of carbon. That means that's a fraction of the mass of C6H12 that is from the carbon atoms. And you'll notice that even though there are fewer carbons, they make up the majority of the mass in C6H12 because each carbon is heavier than each hydrogen atom. That's a good question. Are there units? You're dividing grams per mole by grams per mole, so no, cancels out. So if I wanted to say what the mass percentage of carbon in C6H12 would be, what would I do? Percentage. Multiply by 100%. So this would be 0.8560 times 100%. And that would give me 85.60%. So this is mass percentage. And the way you would say that is C6H12 is 85.60% carbon by mass. Not by volume, not by number of atoms, by mass. Carbon contributes 85.6% of the mass in C6H12. Any questions about this? All right. Just waiting for the last few people. All right. I would like you, we're just going to start out simple. What is the mass ratio of hydrogen in H2O? That's a question mark. And what is the percent hydrogen by mass in H2O? So start with those. What? I know. I'm sure they're like, who is that student teaching that class? I will be 27. I know. Pros and cons to being in this room. Okay, so what do we have for our mass ratio? What goes on top? 1.008 grams per mole. And on the bottom, 2 times 1.008 grams per mole plus 16.00 grams per mole, because that is oxygen. And what did you get? What's your mass ratio? 0. What? 1120, something like that. So that's your mass ratio. And what is your percentage? 11.20% hydrogen by mass. So once again, hydrogen, even though there are 2 of them and only 1 oxygen, hydrogen is very, very light. It's not very massive. And so it does not contribute a whole lot of mass to the to water. Okay, let's use mass ratios in conversions. I could say how many grams of carbon are in 16.5 grams of CCl4. Actually, I'm going to change this. I'm going to do Cl. How many grams of chlorine are in 16.5 grams of CCl4? So there are 2 ways we can do this. We could use our molar ratio, but we could also just use and go through the steps with go from grams of CCl4 2 moles of CCl4, 2 moles of Cl, 2 grams of Cl. But what you can also do instead is just start with 16.5 grams of CCl4. And what you're going to do is say, okay, if I have 1 mole of CCl4, how much chlorine am I going to have? So how much does 1 mole of CCl4 weigh? We're going to have to add it up. Okay, so you add 12.01 plus 4 times 35.45. And that gives you 153.81 grams of CCl4. And out of that 153.81, how much is chlorine? Four times 35.45, which is 141.8. So you're saying, so for every mole of CCl4, which weighs 153.81, you have 4 moles of Cl, those weigh 141.8. And that is gonna, and when you do that math, it's going to give you 15.2 grams of Cl. I'll show you the longer way in case you want to do it this way, but I like this shorter version because you're just doing a ratio. You're saying, okay, so for every grams of the total, you have this many grams of Cl, and you can just, and then you just multiply by that ratio to get how many grams of Cl and 16.5 grams of CCl4. So the longer way you can do this is you can go from grams of CCl4 to moles of CCl4 to moles of Cl to grams of Cl. And you would have 16.5 grams CCl4. And what's your molar ratio here if you use their molar ratio? Oh, sorry. I need to go 2 moles first. Forgot that step. Okay, so now if we're getting from CCl4 to Cl, what's our molar ratio? 4 to 1. Yeah, because you have 4 moles of Cl for every 1 mole of CCl4. And then you're going to get to grams of Cl by saying 35.45 grams of Cl is 1 mole. And guess what? This gives you the same exact answer. You can do this either way. If it makes sense for you to go from grams of CCl4 to moles of CCl4 and then back to moles of Cl, you can do that. That's how you would do it if you use our the diagram that we talked about last time where with all those arrows. Or you can just use a molar ratio, a mass ratio and say, well, for every mole of this, I have this many grams. I'm good. So you can choose. I like this version because it's a little shorter, but this kind of goes through the molar ratio and those steps according to that diagram we wrote out last time. In this case, you have to be sure that so you take into account the 4 moles of Cl, and every 1 mole of Cl weighs 35.45. So don't put a 4 down here because every 1 mole weighs 35.45 grams. Questions? Yeah, what's up? Significant figures, you have 3 significant figures here. Molar ratios are exact, and that's 4 significant figures, 5 significant figures, so your least is 3. Same with this. 4 and 5, your least is 3. Yeah, so it'd be 3 significant figures. I would like you to figure out how many grams of Fe in 22.9 grams of iron 3 oxide. So in this case, it would be 2 times. What do I start with? 22.9 grams of iron 3 oxide. And what goes on the bottom? 159 point what? 7 grams of Fe2O3. And what's the total mass of iron in 159.7 grams of Fe2O3? 2 times 55.85 or 111.7. Yeah. Which gives you 16.0 grams of iron. So yeah, you have the 2 times the iron, so that goes on the top, and then the total mass goes on the top. Oh, sorry. Oh, the 6, yeah, 3 there. Yeah. Any questions, concerns? Can we move on to empirical formulae? Yes. So an empirical formula is the lowest ratio of elements in a compound. And I know that in ionics, we always have the lowest ratio, but that's not always the case for molecular compounds. For molecular compounds, we will often have a lot of carbons, hydrogens, oxygens that are in higher ratios, or that are not fully reduced ratios. So the molecular formula, for example, if you have something like, I call molecular formula MF and empirical formula EF. So if you have something like hydrogen peroxide, which is H2O2, what do you think the empirical formula for that is? It's the most reduced ratio. HO, because you can divide both of these subscripts by 2. HO. C6H12O6, that's glucose. What is my empirical formula of glucose? CH2O, if you divide all of those by 6. Okay? And you can have a lot of compounds that have the same empirical formula. For example, C6H12, C11H22, and C2H4 are all CH2. But these are very different compounds because they're longer chains of carbon and hydrogen. Any questions on this? Yeah. Yeah. So there you go. Now, these are called empirical formula because the scientific process is sometimes called the empirical process, where you go through, you look at your data, and you make a determination based on the data you get directly. That's empirical evaluation. Now, this is really how chemists back in the day, when we were first establishing the periodic table, learned to establish the breakdown of a compound, is that they would cause it to decompose into its elements, and then they would weigh the elements. And once they knew that carbon was 12 times more massive than hydrogen, they were able to say, oh, well, I have this much, this is my ratio because I have this much carbon to this much hydrogen. I know that this is my molecular formula. This is how they pieced it together. So we are going to be able to do that using masses that I give you. So the way you determine an empirical formula is you take the masses of elements in a compound. So for example, a compound consists of 12.25 grams of nitrogen and 28.0 grams of oxygen. What is the empirical formula? Now, you can't just take you just can't compare the mass of nitrogen and the mass of oxygen, because they are different elements. They weigh different, so weigh different masses. So you can't just say, oh, well, nitrogen to oxygen is this much. You have to first turn it into you have to find the molar ratio, and then you can determine the ratio of your compounds in your, ratio of your atoms in your compound. And remember that they have to be whole number ratios, okay? So your first step is going to be find the number of moles of each element. And so what I'm going to do with nitrogen is, how do you find the number of moles from grams? What's your conversion factor there? What was that? Molar mass, yes. So you're going to start with 12.25 grams of nitrogen. And for every 1 mole of nitrogen, that weighs 14.01 grams. And that's going to give you 0.874 moles of nitrogen. Now this step, the significant figures keep more versus less. I would keep at least 3 to 4 significant figures because it's going to help you figure out your ratios later. Don't cut off the significant figures to 1 or 2. Keep at least 3 or 4 here. And if you figure out that how many moles of oxygen you have, 1 mole O to 16.00 grams of O, that gives you 1.75 moles of oxygen. How do you find a ratio? How would we find the ratio of these two? Dividing them, exactly. In this case, we have to have a whole number ratio, which means that we're going to have to divide this by itself in order to give us 1. And then we're going to divide this by 0.874 to give us 1, 2. So it has to be a 1 to something ratio. So we're going to take, so divide by the lowest number of moles to find the ratio. So you're going to take 0.874 moles of N over 0.874, and that's going to give you 1.00 N. And then you're going to do 1.75 moles of O over 0.874, and that's going to give you 2.00 O. Our third step is we round to nearest whole number if it's within 0.1. And what I mean by that is if you get like 2.5, you're not going to round it. I will tell you what to do with that later. But if we round these two numbers to the nearest whole number, we get 1 and 2, right? They're actually exactly 1 and 2, so we don't even have to round. But what that tells you is that we have 1 N and 2 oxygens, which means our empirical formula is what? NO2. That's your empirical formula. Questions on this? We're going to add more steps and more complications. Brandon, you have a question? So is it we'll talk about what happens when it doesn't. A lot of the times it will. Sometimes I won't always, actually, yeah, let's do another example like this. But you can have more than 2 elements And I might not always give you the mass of that last element. I might give you the mass of the compound and say it breaks down into these elements. So I would say 37.97 grams of a compound breaks down into 13.96 grams iron and 8.01 grams sulfur. The remainder is oxygen. In order to find the molar ratio, what do you have to do? Figure out how much oxygen, how do we do that? Yeah, you add the iron and the sulfur and subtract it from 37.97 because in these type of reactions, you're not going to lose mass, you're not going to gain mass, it's conservation of mass. So if it breaks down, you're going to get, the products are going to weigh the same as what you started with. So 37.97 minus 13.96 plus 8.01 gives you 16.00 grams of oxygen. Now we can do our first step of the empirical formula, which is what? Find the number of moles of each element. So we do 13.96 grams of iron. For every 1 mole of iron, you get 55.85 grams, which means that you have 0.250 moles of iron. 8.01 grams of sulfur gives you also 0.250 moles of S. And finally, 16.00 grams. Oxygen happens to be the molar mass of oxygen. So that's going to give you 1.00 moles. So some of you can already probably figure out the molar ratio just based on what you're looking at here, because these do divide in. You can choose to divide by this one or this one because they're exactly the same. They're both the lowest. So you're going to divide by 0.250, 0.250, and 0.250, which gives you 1 iron, 1 sulfur, and 4 oxygens. What is your empirical formula? FeSO4. Can anyone tell me what that's called? Iron, 2 sulfate. Yeah, what's up? Of course. Yeah, so you have to find a ratio. And so for example, if you were trying to find the ratio, so say you had a class that was 75 women and 25 men, okay? That ratio, you divide both those numbers by 25, you have a 1-to-3 ratio. So to find a 1 to something ratio, you divide by the smallest amount, and that's exactly what we're doing. We're dividing by 0.25, so we get 1, 1 to 4, 1 to 1 to 4 ratio. Yeah. Only in this case because the smallest amount is 0.250. In the last one, we divided by what did we divide by? 0.874. So it depends. The smallest amount will change. So you can also find empirical formula from percentages. So I could say a compound is 25.9% nitrogen and 74.1% oxygen. What is its empirical formula? You don't have grams here, so how do you figure out how many moles? The great thing about empirical formulae is that they will say the same. It's the same ratio of elements, no matter how much of that compound you have. So what we're going to do is we're just going to assume a certain amount, a certain mass. We're going to assume 100 grams because that's the easiest. Because if it's 100 grams, how many grams of nitrogen do we have? 25.9. And how many grams of oxygen do we have? So you just turn those percentages into grams. So you have 25.9 grams of nitrogen. 1 mole of N is 14.01 grams. That gives you 1.85 moles of nitrogen. 74.1 grams of oxygen will give you 4.63 moles of oxygen. So Danielle, in relation to your question earlier, in this case, we're going to divide by the lowest, which happens to be 1.85. Okay? So we're going to divide by 1.85 and 1.85, which is going to give us 1N and 2.50. You can't round 2.5. What was the rule for rounding? Within 0.1. This is not within 0.1. You can't round it up to 2. You can't round it up to 3. So what we have here is we have what we call pseudo subscripts because they have to combine in whole number ratios. Okay, so these are the pseudo subscripts. How can we make these pseudo subscripts into real subscripts so that everyone's a whole number? Multiply by 2. Now, if we multiply this guy by 2, what do we have to do this? Multiply by 2 because we want to keep the same ratio. So we have to multiply everything by 2. So it's times 2, which is going to give us N2O5. It's like when you have a fraction. A proper fraction has a whole number on the top and a whole number on the bottom, right? When you first learn fractions. So 1 over 2.5 is not technically a proper fraction. So in order to make this a proper fraction, we have to multiply both the top and the bottom. 2 over 5. That's exactly what you're doing here. You're taking everything and you're keeping the ratio the same. 2 to 5, 2 to 5. Questions? All right. Let's do molecular formula from empirical formula. Sometimes I will give you the molar mass of a compound. in addition to its individual components. And then I will ask you, what is the molecular formula? Hint, you can't directly find the molecular formula without finding the empirical formula. So what we're going to do is we're going to do our empirical formula like normal. So we're going to ignore this for the first part of the problem, okay? So based on the fact that we're ignoring this, what's my first step? First step of finding empirical formula. Find the number of moles from 2.231 grams carbon and 0.0388 grams hydrogen. Okay, just start it like we did with all of the other ones. And this is going to give you 0.0192 moles of carbon. And it can be a small amount. This is okay because remember the ratio of these elements is the same no matter if you have a kilo of it or 0.05 grams of it. It's going to be the same ratio, okay? And we take 0.0388 grams of hydrogen. I'm going to turn that into 1.008 grams per 1 mole of H, and that gives us 0.0384 moles of hydrogen. Now, what is our lowest number? Yeah, that one, the one on the top. So we're going to divide both of these by 0.0192. And that's going to give us 1 carbon and 2 hydrogens. So what is our empirical formula? CH2. But that's our empirical formula. That's not what I asked for. I asked for our molecular formula. Our molar mass tells us how many times we have to multiply these subscripts in order to get our molecular formula. Our molecular formula is some multiple of this formula, okay? Sometimes your molecular formula and your empirical formula are the same. You know, like for example, Fe2O3, you can't divide that anymore, so your empirical formula and your molecular formula are the same. In this case, we have to figure out whether we need to multiply this by some factor to get our molecular formula. We're going to do that by comparing the mass of the molecular formula to the mass of the empirical formula and seeing how many times it goes into that. So I need to figure out what mass of my empirical formula is, or my empirical mass is what I call it. So what is my empirical mass? Can anyone tell me that? No. So that is the amount of the compound we have, but I'm talking about this empirical mass is the molar mass of the compound. So 1 mole of this. Yeah. 14.03. How do we figure out how many times to multiply this? How do we compare these two? Divide. Divide which by which? What's your numerator? Molecular mass over empirical mass. Okay? which gives us 84.18 grams per mole over 14.03 grams per mole, which gives us 6. This is our multiplying factor. If you do not get very close to a whole number for this, you did something wrong. Your empirical formula is wrong, or maybe you flipped them. This should always be a whole number. These are sometimes not whole numbers. This should always be a whole number. So based on my multiplying factor, what is my empirical formula? I mean, what is my molecular formula? Beautiful, C6H12, because you have to multiply the whole thing by 6, which gives you C6H12. That is your molecular formula. Questions, concerns? (12.01 plus 2 times 1.008 gives you that. It's the molar mass of this, of your empirical formula. Oh, it's significant figures, because 12.01 is specific to the hundredths place. So your answers. You'd still get about the same answer, or you'd probably get 6.00 something. Would you like to do a practice one? 3 people just shook their heads. Okay, we're gonna do a practice one. Chris. Raise your hand if you need help. Yeah, so you see 120 on the top. This is photo right there. Yeah, and you didn't even have to turn that. You could have just turned it to 39.5. Yeah, because you can see you're here. You're assuming 1 gram.
Oh yeah.
You could just assume 100, but this is fine. It just is an extra step. Okay. It'll get you the same place. Just make sure you do that for all of them. Okay. Yeah, it comes. So when you trying to figure out what order you're putting it, just put it in the order of that I gave you the element. So it should be C, then H, then N. Just put it in that order. Carbon almost always comes first if it's like a CH something. But Okie dokie. What do we have to do? Where did my pen go? Here we go. What do we assume? What's our assumption in this case? Percents are equivalent to the grams. We assume 100 grams. So we have 39.95 grams of carbon, and we're going to turn that into moles. And that gives us 3.33-ish. And 13.44 grams of H. Gives us 13 point something. What is it? 13.3 moles of H. And my last one is 46.61 grams of nitrogen, gives us 1 mole N, 14.02 grams. And that also gives us 3.3-ish. 33-ish. So what are you going to divide everything by? 3.33. Which gives us approximately 1, 4, and 1. So what is our empirical formula? CH4N. But that's not where we stop. We stop at molecular formula. So what is my molar mass for my empirical formula? What's my empirical? Oh, what's the question back there, Ruby? For this one, the significant figures, yeah, like you don't really, I mean, as long as you have 3 or 4, for this point, I'm not going to count, like, because you're going to turn them into ratios anyway. Sig figs don't, more sig figs is better, but I just generally keep 3 to 4. And so I don't really care about sig figs in this case, as long as you keep at least 3. But yes, you are right. It would be 4 sig figs. Yeah. That's fine. It would get you to 1, 4, and 1. As long as it's within 0.1, you can round it. Yeah. So you may not get exactly 4 for that. You'll get 4 point something. But as long as it's within 0.1, you can round it. So if it's 3.99 or 4.01, that's fine. You can round it to 4. That should also be within 0.1 of it. Yeah. So it should be pretty exact. I can't always make it, like, if I had like a lot more sig figs, I would make it exact. It should be almost exactly a number. Maybe not quite exactly a number, but almost. Okay. So what's our molar mass of CH4N? Sorry, what was that? I can't hear anybody. Was it 60.06? No, 30.06, right? Am I completely crazy? 30.05-ish? Okay. So when you divide 60.12 over 30.05, you get almost exactly 2. Which means, so you can round that. It should be very close to an integer, but you can round it the teensy bit. But like if you got like 2.5 for this, it would be wrong. You know, it should be like 2.0 something, you know, 1.99. So then what's my molecular formula? Congratulations. Have a great spring break.